Okay, welcome back. I would like to go through the code briefly, or not briefly, but completely. At least through the whole car rental exercise F. I won't go through the exercises A to E because once you completed F, A and E are not necessary anymore. And after that, we will go to another topic, but we'll directly come back to the Jane's car rental exercise. So if you haven't finished the code, you can either complete the code yourselves then, or download the code which is on the LearnWeb and work with this code on the next exercise. All right, the code for the Jane's car rental exercise is the following. I hope that you can read everything. First of all, we initialize everything. We initialize the action value function as 380 plus 10 times the cars in location 1 plus 8 times the cars in location 2. And the reason for that is that a car gives us a reward of an instantaneous, a rental gives us an instantaneous cash flow of 10 in either location, but we receive many rentals in location 2, but not we receive many return cars in the second location, but not many rental requests in the second location. So a car in the second location is obviously worth a little less than a car in the first location. So that's the reason why the action value function is initialized as this in here. We also need to initialize the policy. Of course, the policy has the same dimensions as the action value function because it gives us a probability of taking an action at a certain level of cars in the first location and a certain level of cars in the second location. And then after that, we of course needed to set all the points where we must not end up to 0. So both the action value and the policy, because if the policy is 0, then we will never choose one of these actions. So we will never end up in this new state, and thus we will not compute a new action value for these states. So everywhere where the action value function is 0 after the algorithm has converged, these are then again the states that never occurred and are impossible to occur. Then I additionally initialized two matrices, one of the value function, so not the action value function anymore, but just the value depending on our current state, and the greedy policy matrix, which is a matrix that shows us what is, at our current knowledge, the greedy policy. These two matrices are only for plotting later on. So they are not necessary for the task, but they're very convenient tools to plot value function and the policy later on. Because we are only, of course, interested in the greedy action. We don't really care about all the other actions because all the other actions have the same probability. Then we initialize the cost of moving a car from A to B, the car revenue, so the revenue we earn on renting a single car. Our discount factor is initialized. We have a sequence here for both alpha and epsilon. So alpha is decreasing from 0.25 to 2 divided by the log of the current point in time, and that squared. So it doesn't really fulfill the conditions for convergence, but it's close to these conditions, and it ensures that the decay of the learning rate isn't too sharp, so we will still learn after several episodes, after several iterations. But if we would run this for an infinite amount of time, this wouldn't converge, I think. But then again, continue to fluctuate. For our example here, we don't need perfect convergence. It's just this example is just to see that the algorithm works and selects and learns both the value function and a policy. And epsilon decreases as well from 0.25. So in the beginning, we deviate quite a bit from the optimal policy. And in the end, the deviation from the optimal policy will become very small. So we also learn a policy that gets better over time. Then, of course, the cars in the evening in the first day are the same as the cars in the morning because nothing has happened yet. And the state that's important here is always the cars in the evening. Cars in the morning is just an auxiliary variable that allows us to do all the computations in many small steps instead of one very large step. So let's just run these lines of code up to there. Right. Then let's go into the loop and learn the value function. First of all, we select an alpha, the alpha of our current iteration. Epsilon, for epsilon we do the same. Then we need to compute the cars in the morning, and these, of course, depend on the cars in the evening of the day before and our old action. The first old action had to be determined once, so single time before we go through the loop. So we do that here in line 39. Once we determined how many cars our both locations have in the morning, we can then simulate the number of rental requests in A and B and simulate the number of rental returns in both locations. And based on the rentals of both locations and the revenue we generate from a single car and from our old actions, so how many cars do we move from A to B or from B to A, this multiplied by the cost of moving a single car will then constitute our reward of this iteration. Once we've computed the reward, we can also compute the number of cars in the evening at both locations. It's just the number of cars in the morning minus the number of rentals plus the number of returned cars. And we take the minimum, the piecewise minimum of this term and max cars, which is set to 10 because we're only allowed to have 10 cars at each location. So this is just simulating the rental. Then also just simulating is select the new action. So at the evening of day 2, we select what we are going to do in the next day. And we sample here again from our set of actions a single time with the probability equal to the policy of our current state, meaning our current cars in the first location and the current cars in the second location, both times here +1, because we need to shift from the values of cars to the index. In here +1 because we can have 0 to 10 cars, and the indices are 1 to 11. Once we did that, we can compute the delta, and I'm also storing the deltas here. That's not necessary because we can also only compute the temporal difference error once and override it each time. It's the reward plus gamma times the action value function as of tomorrow, so with the cars and in iteration I at both locations, and the action we are going to execute tomorrow. And we subtract from this the current value function, meaning the AVF at the current cars in location 1, the current cars in the yesterday's cars in both locations, and our old action. We can use then this delta to use the update rule from, I think, slide 24, to update the action value function as of yesterday, just by taking the old action value and adding alpha, so the current value of alpha, that depends on time as well, as you can see in line 46, times these deltas. That's the update for the action value function, and after we have updated the action value function, we can then first of all, we can override the old action with the new action, because tomorrow what we chose yesterday will be then our old action. So what we execute is the old action. Then we will decide again for a new action and then override these again. So this actually is, this line here is one of the most important lines, because this one switches always the new action to the old action, so we can iterate from that at the next day. And now we only need to only need to update the policies, and we need to update 3 types of policies. We need to update the impossible policies. Well, we don't really need to update these because these are already 0. We don't need to set them to 0 again because they don't change. But we need to know which policies are impossible. We need to find the greedy action. So the action that maximizes our new action value function. And we need to find the non-greedy actions, so the rest, all the other actions, and to distribute the epsilon probability equally to these other actions. So let's first of all select the null policies. So that's simple. All the policies that are equal to 0 are our null policies. We must not, at any point in the code, must not put any probability to these policies, because once we get stuck in a null policy, everything will break down and nothing will work anymore. Then we can select the greedy action using which_max, so giving us the maximum of the action value function of the number of cars we currently have, we had yesterday in both locations. And we get the non-greedy actions, which is just the remaining actions. So all the actions, we exclude the null actions and the greedy action, and we add +6 because we are interested in the indices, not in the actions themselves. So this gives us the new indices. And then we only need to set new policies. The policies at the non-greedy actions is equal to epsilon divided by the length of the non-greedy actions, because we can have different amount of non-greedy actions depending on how many actions are impossible. If we are at the point 0, 0, 0, 0, meaning we have no cars in either location, of course, many of the actions are impossible, so the probability epsilon is distributed among fewer actions. And last but not least, we can compute the policy or the probability of using the greedy action as 1 minus epsilon. So in the first iteration, it's 0.75, and the second iteration, it's 0.8, I don't know. And this will increase, of course, over iterations. Once we did that, we can compute the action value, the value function as the, we can compute, this one here is the mean over time of the action value function, which is a nice indicator whether or not the algorithm converges, at least whether the level of the value function converges. So if this one is gets constant over time, then you obviously see that at least in level, the value function is converging. The value function then is, of course, the weighted average of the action value function, where the weights are the policies. So the greedy policy gets much weight, the action value function of the greedy policy gets much weight, and the others get less weight. And then we can also select the greedy policy of all the of the whole action of the whole policy cube, and we can plot that. So let's just run this code and look what's happening. And of course, as I said, this code takes a couple of minutes to run. So we are looking at the first 250,000 observations when the plot is going to be there the first time. So as you can see already, the value function has had the first update. On the top right, we have the highest value, and the bottom left corner, we have the lowest values. And as you can see, after 500,000 iterations, the value function already has a shape that is pretty similar to what we will see after 10 million iterations. The policy, on the other hand, is much noisier, and it will be much noisier all the time. So although the value function already looks pretty decent and pretty smooth, the policy function will be much noisier, and we will not see a smooth policy function here. And as you can see, in the lowest plot, and the lowest plot, the average of the action value function decreases over time, and in here at 1.5 million, it is already not decreasing very much anymore. So after this number of iterations, the action value function is close to its convergence, but the greedy policy, or the policy function, of course, as you can see here, hasn't converged yet. So if we run this for 8 million more iterations, we will see what happens in a minute. Are there any questions so far to this algorithm? Yeah. Yeah. That means 0.4 of the 40% of the 11 values you could choose between in the cars. So this is the cars in the first direction, and the epsilon and the y-axis you have the cars in the second direction, but not the numbers from 0 to 10, but just the share of going from 0 to 1. So this is just a relative measure here. The image command always scales down both axes to being from 0 to 1. It's just an R-specific feature. We would, of course, like to see 0 to 10 and 0 to 10 here. And then the brighter the greedy action, the lower the value, and the darker the greedy action, the higher the value. So if I have cars, if I am in the bottom right corner, I only have cars in the first location. I don't have cars in the second location, so I move cars from the first to the second. And that is what the dark red color is indicating. So this is just, yeah. And on the opposite, in the value function, of course, if I have many cars in the first locations, many cars in the second location, so I'm at the top right corner, then the value function is very high. And if I have no car in both locations, in either of the locations, then the value function is very low at the bottom left corner. Yeah.
So you would like to have a three-dimensional plot, and these are like slices to this three-dimensional plot. Is it something like that?
Well, the rule that what do you want to do in the end is not three-dimensional anymore, because you have a state of cars in the first location, you have cars in the second location. Based on that, of course, you always want to do the greedy action in the end, once everything has converged. So that's not a three-dimensional problem anymore, because the probability will converge to a point probability of 1 for one of these actions.
Yeah, but these are, at the end of the day, three numbers, right? I mean, the state that I'm in, these are two numbers, and
Yeah.
what I want to do is a third number.
Yeah, and the third number is the color.
Pardon?
The third number is the color. So the darker the color, the higher the number. The brighter the color, the lower the number.
Okay. But I mean, going back to if I want to, take a stand on how many, then I cannot.
Not with this plot. No, not with the plot. But if you look at this function at the GPOL matrix, I can just stop learning right now. Then you can look at the GPOL matrix, and then this matrix will give you the actions. So in the top left corner down here, that is the where I have where I have 10 cars in the first location and 1 car in the second location, and 0 cars in the second location, and this is the bottom right corner of the matrix, of the graph here. So 10 cars in the first location, 0 car in the second location, and then I will do action 11. And action 11 is shift 5 cars from the first location to the second. On the other hand, if I have 10 cars in the second location and 0 cars in the first location, I choose action number 2, which is to shift 4 cars to the first location.
Okay, so that will be your plan, basically.
Yeah, this matrix is our plan.
If you would be consulting Jane, you would just give this, after many iterations, you would just give this to her and tell Jane, look, this is what you have to do.
Yeah, exactly. Hope much. Depends on her current policy, I think. We can, of course, compute that. I mean, if we compare the value function of this to the value function of a random policy, then we should know what she should be willing to pay. Yeah.
Pay for the advice, for the consulting.
Yeah, sure.
Yeah, true.
Okay, there's in the second line of the credit policy, in the matrix here, element number 9 is set.
Yeah.
Which is really out of touch with the other values here.
Yeah.
How come that doesn't change?
This is a situation where we have a single car in the first location, which is the location where all the cars will be returned to, I guess. And we have not much rental requests. And we have 8 cars in the second location, the location where we have many requests but not many returns. So a situation that occurs very rarely because we have very many returns to the first location and very many rentals from the second location. So situations where we have many cars in the second location but only a few cars in the first location, they don't occur often due to the law of motion. So this 7 will stay here for quite some time.
So the 7 is really far away from the optimal action in that case, but it doesn't matter because this situation won't occur anyway.
Yeah.
Right. And another question, one of the advantages of the SALSA algorithm is that you are learning on the fly.
Mm-hmm.
Say, you're actually learning while the process is going on. But we can say here that it took about 4 million iterations, or say 2 million iterations until convergence. And if one step to 1 day, that's a few thousand years.
Yeah.
So we finally learn the optimal policy. So this is a very academic statement that the advantage of this approach is that you can learn on the fly.
If you have daily data, then yes. If you have high frequency data, then you could learn on the fly first. And second, if you have data, the point here is that you could generate much more signal from the data than is by using each data point just once. So if I have a representative sample of 1,000 days of this car rental, then I could run the whole algorithm with these 1,000 points several times. I would, of course, not get a perfect picture because then even more situations will never happen, of course. But I could also, and we will, no, we're not working with data actually, but you could run the algorithm with the same data over and over. So run many epochs of learning as it is, for example, done in when you train a neural network to detect handwriting or something. Then you
By the same token, I mean, I would agree in the sense this is a little bit of an academic exercise, which is not bad in itself. But I mean, again, for practical reasons, suppose you were Jane, and wouldn't there be a much better idea to have some observations, estimate the Poisson processes, and use this information and the value function iteration to find the optimal policy?
Yeah, I think so, because the example is so simple, yes. So, of course, if we have this simple Poisson process, and if we only look into these 2 states, which is ridiculous, because if you run a car rental, you would look into many, many more states, like whether there are holidays, how the weather is, so much more so many more variables determine the rental requests of a car rental. So in reality, this example is, of course, oversimplifying. Okay, any further questions?
So the assumption of having a Poisson process for the number of rentals and returns, that's just to make this operational. Yeah. It's not really, it's not necessary to assume anything about the generative process, stochastic process that gives advantage, I think.
Yeah, I think so too. It should be in some way stationary, I guess. Because otherwise we would learn something about states that doesn't matter in a couple of weeks. But besides that, yes. Okay. Then let us continue. But just give me a second. I need to find something. In a minute or so. There we go. Okay, let's continue with the lecture with some slides. So what we have done so far is we updated our value function, or in this case our action value function, by following some epsilon greedy policy we derived from the action value function. So we did that iteratively in order to get the optimal policy. A problem here might be, or is, that we are learning the policy, and with it the action value function, by using the very same policy. So we are either learning a policy that explores much of the state space, but then the policy is far from being optimal, or we learn a policy that doesn't explore much of the state space, so maybe misses very important states and very important features of the state space. So in this case, the policy might be optimal to what we know, but the policy might lead to a case where we don't have enough knowledge of the state space in total. One solution to this problem, so to this trade-off between the large epsilon, so learning much of the state space but not getting the optimal policy, and the small epsilon, so having a greedy action that isn't really the optimal action, is to use off-policy learning. Ignore the text here, it's the same learning lottery setup that we have had before. We have a number of lotteries, we invest a token, we play the lottery, and we get a reward, we can play the lottery again, and so on and so on. So let's have a short look at this Shiny app that you have already seen before. So this is the Shiny app that we've seen, and this Shiny app allowed us to learn something, showed us how well we could find the optimal policy in this lottery setup. And let's just have a look at this here. We have a deviation from the greedy policy in log scale, so it's e to the power -5 and so on. Let's just run this once. We have a deviation from the greedy policy that is 0.5% roughly. We have learned over 20 episodes, and we have learned a value function. And we have seen that if we increase the number of episodes, and if we increase the deviation from the greedy policy, we can, of course, make sure that we learn the correct value function, or at least get closer to the optimal value function. And if we increase both even further, then we can, if we learn this a couple of times, we see that in most cases here, we end up with the perfect or with the optimal policy. But in both cases, we end up sometimes with policies that are not optimal. And additionally to that, due to our deviation from the greedy policy, we lose return over time. So we lose money that we won't get by deviating from the optimal policy. Okay, now you should see everything. So at least everything that's important. That's because we learned the same policy that we applied to learn the policy. One way to get rid of this is to use off-policy learning. That is, to introduce a policy that determines our behavior while we are learning, and the classical policy pi, that is the policy that we actually want to learn. So we want to learn a policy here that doesn't really deviate much from the greedy policy. So we want to learn a policy that is very close to the optimal policy. We don't want to spend that much time learning, so we decrease the number of episodes to 20. And now think of that we now use a policy that deviates quite significantly from the optimal policy. So we learn the optimal policy or policy close to the optimal policy by using a policy that deviates from the optimal policy quite often. So let's increase this to 1 and let's learn with this policy, learn 100 times. And we see that with this, so let's deviate a little less. We can see that with this, we very often learned the correct policy and increase the number of steps, sorry. So what we see is that very often we learn the perfect policy much more often than we would with this rate of deviation, because the deviation policy of the policy we want to learn is now basically 0. So we can't read this probably, but this is basically 0. The off policy, on the other hand, deviates with 13%. So the policy that determines our behavior while we are learning. And after we said that we converged, we can say, okay, now we switch from the behavior policy we used to learn the value function to our now optimal policy. And from this moment on, we exploit the state space and we exploit the situation. So we are learning two policies. And these two policies not only differ, of course, in their epsilons, they are both epsilon, at least epsilon soft, with different values of epsilons. But these different epsilon values might also return in choosing different actions. So learning the action value function with an epsilon greedy policy and epsilon is 20% does not necessarily give us the same decision as learning with an epsilon greedy policy of epsilon being just 1% or 0.1%. So to say that I could also learn the state space or learn the value function with a epsilon greedy policy that deviates much, and after that I take the same policy, so the same, in this case in Jane's car rental, the same cube, and I switch every deviation probability of 20% by a deviation probability of 1% might be inconsistent because we might then decide for the wrong action. So the epsilon parameter isn't the only thing that changes if I change the level of greediness in my policy. It might also change the whole policy in total. Having that in mind, we can see, and we will see, that this is not the case if I use off-policy learning, because I will update my my value function by incorporating both of these policies at the same time. And the way we do this, I can show you this in a minute, is by using The behavior policy that we have just seen is more epsilon greedy or has a higher level of deviation. And the behavior policy is, if you look at code, it has the same structure than the actual policy we want to learn. And then we can compute the importance sampling ratio that is directly taken from importance sampling, where you sample from a distribution or want to compute the expectation of a certain distribution by using another distribution. And this importance sampling ratio here is the value of the policy we want to learn, so the probability of an action, given we are in a state, of the policy we want to learn, divided by the probability of the same action, given the state, of our behavior policy. There are two situations that we can distinguish here. The first one is our behavior policy explores the state space, and the second one is the behavior policy is actually choosing the greedy action, so it exploits the state space. Let's put some thought in these two situations. If we explore the state space, so this one here is epsilon pi, and this one here becomes epsilon, not epsilon, epsilon divided by the number of non-greedy actions, and this one epsilon b divided by the number of non-greedy actions. Then we see that because the epsilon is much smaller in the optimal case than in the behavior policy case, we see that the importance weight is very low. So we don't learn from those steps where we explore the value function or where we explore the state space. That might sound counterintuitive at first because we only incorporated epsilon greediness to learn something about the state space, but we don't want to learn what happens after exploring, so directly after exploring. So we don't want to know, really, we're not really interested in the effect of the reward of an exploratory step, but we want to see what happens after that step. After we have explored a new state, we want to see what would happen in this new state. So moves to states that are not according to the greedy action will be weighed down quite significantly, and we won't learn from these steps because later on these steps don't matter to us. Later on we won't use any non-greedy actions. So why should we learn about the reward of sending cars from the first to the second location if that never happens in reality after all? On the other hand, if we use the optimal or the greedy choice, we see that 1 minus epsilon pi is larger than 1 minus epsilon b, so the probability of, so this probability here is larger than this probability, so our moves using the optimal or the greedy policy, so the greedy action, sorry, will weight up. So these will have a weight larger than 1, so we will learn more from the steps that we are actually interested in learning from, and we will make more exploratory steps and learn again after the exploratory step what would be optimal in this new state. We need two conditions. We need one condition, sorry. That's the so-called coverage condition. We must ensure that everywhere where the policy we want to learn is larger than 0, our behavior policy needs to be larger than 0 as well. So the denominator here is 0, is never 0. Now let's have a short look to sum up today how to incorporate this into the SASA algorithm, and we can do this super simply. First, we don't choose an action for tomorrow according to policy pi anymore, but according to our behavior policy b. Second, we compute the importance sampling weight just by dividing these two probabilities by each other. So pi evaluated at the new state and the new action, and divided by b, new state, new action. And after that, we multiply alpha by rho by our importance weight when updating the action value function. And that's the single difference between on-policy learning SARSA and off-policy learning SARSA. And off-policy learning SARSA very often works much better, especially in learning the policy, because we can allow the algorithm to deviate much more often than we would deviate in reality by following the optimal policy. Okay, do you have any questions?
Yes, but only a brief one due to time. So basically, what you've assumed before is you implemented some alpha decay on your own, basically. So just out of your head. And what you do now is you implement the same but more cleverly.
It doesn't have to do with the decay of alpha. So this pi has actually, this rho has actually two different values. So either it's exploring, then the value is smaller than 1, or we use the greedy choice and then the value is larger than 1. So we learn more from the actual greedy steps where we actually use the greedy action, and we learn less from the steps where we use the exploratory action, because we are going to learn a lot about the new state tomorrow. But we are not interested in what happens today to our current reward if we choose an action that we will never would never choose optimally in the end.
Thank you.
Okay, then I would say we will start with this and with the exercise to off-policy learning on Tuesday. So have a nice weekend and see you on Tuesday.